All right, welcome to the last session of the morning. Our first speaker is Richard Elliott, who's professor of chemistry in both the University of Oxford and the University of Cambridge. And without more ado, please, Stephen, please start.
Thank you very much, Mike, and thank you for the organizers for this invitation to talk here, present some of our very latest results. So it's a great pleasure to be at this really interesting conference. First time I've been to UAE actually, so that's also good. And the weather's rather good. I looked just before I came out here. The weather in London at the moment is 3 degrees, so this is very satisfactory, really. So I'm going to talk today about the methodology of machine-learned potentials, machine-learned simulations, which actually Mike mentioned in his talk. So there's a brief introduction there. And the applications I'm going to talk about are in phase change memory and switching materials. And Bilge Yildiz gave quite a good introduction, actually, to that before she talked about her materials. So that's also good. But the materials I'm going to be talking about are not crystalline mostly. They're glassy, amorphous, and we haven't heard too much about that. There's a lot of crystal work here, but Rajesh Ganapathy talked about glassy colloids, which is also an introduction to this. So that's the sort of formal title, but perhaps an alternative title might be, what use is a really bad glass? And if you accept this is actually what I'm going to be talking about, you might then say, well, why am I here, right? Talking to Advanced Materials Conference, really. So I tried to persuade you during my talk that actually these materials are quite advanced and quite interesting. So before I carry on, I'd just like to acknowledge the people who did the work. The group in Oxford, Volker Deringer, machine learned potentials and the molecular dynamics associated with that. Colleague Tai-Hoon Lee in Daegu in South Korea, hyperbonding model, DFT calculations, Wei Zhang and Xian on molecular dynamics using machine learned potentials, and Min Zhu and his group, experimental group, actually looking at selector devices. I'll talk about those, and Kostas Konstantino in Finland, who did the work on defects. So my interests mainly are to do with the effect of disorder on material properties. And that leads you naturally to think about glasses and amorphous solids. And in order to understand their properties, particularly their functional material properties, it is not just useful, essential really, to do computer simulations. Because unlike a crystal where you know absolutely what the atomic positions are, of course, and then you can sort of calculate in often really quite simplistic way what the properties should be from a crystal. For a glass, you know nothing about that. So you have to do a lot of simulations. And in the last 5-6 years, I've got very involved and interested in machine-learned interatomic potentials for simulations, and these are interesting because they're linear scaling, unlike DFT, which is cubic scaling. So you double the number of atoms, you only double the time to do the simulations. And the applications I'll very briefly mention silicon structure and defects, but most of the time on phase change materials. And the materials I'm talking about, tellurium and this germanium antimony tellurium material. Okay, so atomic structure of a glass. What do we know, if anything? Well, probably there might be some short-range order. First coordination shell, second coordination shell, bond lengths, bond angles, mostly pretty well defined like a crystal. Possibly some medium range, intermediate range order, going up to say 10 angstroms, maybe preferred ring sizes, dihedral angles, angular twists, and so on. Definitely no long-range order or periodicity, because they're glassy. So we can only describe the structure in statistical terms using correlation functions. There's no unique structure, unlike a crystal. And as I said before, you need models, really, structural models, in order to understand what the atomic structure is and then calculate what the properties are and understand them. So you want to do this modeling, and you want to do computer modeling, and you want probably the best way to do it is using molecular dynamics, where you put the atoms in a box and they interact by some potential, and you can give them energy, you can do it at certain temperatures, reduce the temperature, whatever you want to do. You can look at the dynamics and you can look at the static properties. So you need a potential, and the simplest way is just to use an empirical potential, bond stretching, bond bending, something like that. It is simple, it is quick, and it's not accurate. You can go to the other extreme. You could use as much quantum mechanics as you can get in using density functional theory, complex, slow, cubic scaling, but it's accurate within approximations on what the exchange correlation functional is and so on. Or you can have a compromise. You can basically have what's one of these machine learned potentials, which basically feeds off density functional theory, potential energy surface, as I mentioned in a minute. So you keep the DFT accuracy. It's complex, but it's quick. It's linear scaling. So how do you do this? You have a whole series of models, thousands, tens of thousands of small models with very, very different configurations. Those configurations you think you might find in a molecular dynamics simulation when you're going from a liquid to a glass or glass to a crystal, whatever. And you take all these models and you do electronic calculations using DFT level, and you fit the potential, the electron potential, your potential to the potential energy surfaces using some structural descriptor. The one we used earlier was a thing called SOAP. You need to know about that. So you describe the structure locally, going out to maybe sort of 10 angstroms or so in terms of a general descriptor, and then you map your energy onto that descriptor. And there are two ways of doing this. You can use neural nets or Gaussian regression progression, which is what we used. So these potentials are linear scaling, mostly because they have a spatial cutoff for the structural descriptors, right? And so that's one advantage. Another advantage of the energy is actually the sum of the individual machine-learned atomic energies. So you can calculate these things. You can't observe them actually experimentally, but you can calculate them and use them. So that's all a good thing. The bad thing is you don't get any direct electronic information out at all, wave functions. So this gives you a timeline on where we've been doing in silicon, say, and before about 2018, we could do DFT calculations on about 500 atoms, max. 500 atoms. Could take several months on a supercomputer to do these calculations. 2 nanometer size. First gap model we had was in about 2018, allowed us to look at 4,000 atoms, roughly an order of magnitude more. So this is DFT accurate, but 10 times the size. And then 3 years later, we could make a model of 100,000 atoms, DFT accurate. And then using this model, which is now this one, 13 nanometers in size, is basically teaching the next generation of potential, which is this one, and we can get up to 1 million atoms. Right? 1 million atoms models, all DFT accurate as this one at 500 atoms. So that sounds quite good. But you might say, why big models apart from just bragging rights? Well, my model is bigger than your model, right? So what are the advantages? Well, the advantage is that, of course, if you've got a large number of atoms, you can look at rare events in a statistically significant way. I'll mention that in the next slide. To mention here, I'm going to talk about silicon in the next slide. And silicon is normally 4-fold coordinated, tetrahedral, sp3 bonding. You have some defects. You have some 3-coordinate under-coordinated dangling bonds, or you have 5-coordinate, an extra atom, interstitial atom comes in. So people knew about this, not many of them, fractions of a percent, but they didn't know what the geometry was. Everybody thought it was this floating bond, a tetrahedron with an interstitial silicon coming in. Actually, we found in this 1 million atom model that there are 3 types of geometrically different types of 5-coordinate defects, which you can only find out if you've got the statistics. What else might be interesting? Well, if you're looking at, in this case, this is pressurized crystallization of amorphous silicon at 20 GPa, you go to simple hexagonal silicon and look at, this is 12, 13 nanometers size, and look at the size of the crystals you generate. Of course, you can't understand this crystallization here if you've only got a very small model, basically. And also, there are others too. Of course, the bigger the model goes, the fewer boundary effects there are, size effects, and so on. Hello at the back. This doesn't seem to be working anymore. Right, it does. Good. So this just one slide to show an advantage of these really large models. A 1 million atom silicon model. I've mentioned these 5 coordinate defects, and there are only about 1% of them. In 1 million atoms in the model, there are only 10,000 of these over-coordinated 5 units, which are independent, which are separate. So if you've only got 1% and you've got a DFT model of 500 atoms, you've only got possibly 4 or 5 of these defects there. You can't, in the very small model, you can't get any statistics. Here we've got 10,000 to look at, but actually we found that most of them are separate, but actually quite a lot of them cluster. And you have clusters of 2, and you have clusters of 3, and you have clusters of 4. And in this 1 million atom model, we just found 200 only of these 4 coordinate ones, right? So we can look at these very rare events in these very large models. And this also slide also shows the advantage of this thing which you don't get in DFT. You can't do this in DFT simulations, actually ascribing energies particular type of atoms. So here's the energy scale going from very low to very high, and in this dimer of these 2 5-coordinate defects, this is the highest energy site, which actually is the bridging silicon between the 2 5-fold coordinate. So we've got all this local information that we can get. This clicker isn't working, actually. Hello, at the back. Could you just change the slide for me, do you think? Yeah, that's good. So I'm going to talk from now on about these phase change materials, which Bilge mentioned. And I should say, if you do a Google search, you might have done before this talk, what is a phase change material, you find actually there are 2 meanings in the literature. So caveat emptor here, right? I'm talking about phase change memory switching materials. If you go down another rabbit hole, you find that phase change materials refer to energy storage materials, those like salt hydrates, sodium thiosulfate or something, where the latent heat stored or released at phase transitions you just use as a heat source, basically. These are nothing to do with these, right? So I'm only talking about these phase change materials here. Sorry, could you change again? This is very boring, actually. Thank you. So what are the characteristics of the materials I'm going to be talking about? They are materials with very different physical optoelectronic properties of the 2 structural phases. These materials can be switched reversibly between phases. So we could go from a crystal to a glass to a crystal. We could go from a crystal to a liquid to a crystal again in a sort of cyclic way. I should say, going from crystal to glass, which I'm going to be talking about, you don't go directly. You go from a crystal to a melt and quench the melt to the glass, and then you go directly from the glass to the crystal. And obviously this, you just go crystal, liquid, crystal, and there's no glass intermediate here. How do you do this? 2 ways. You could switch them by applying a voltage, Joule-heating voltage, or a short optical pulse. And the point is that you can always melt a crystal unbelievably rapidly. Right? If you put a huge amount of power in a very short time, you can melt in picoseconds, basically. So the rate limiting time is not the crystal liquid or crystal glass, and you can quench that liquid very quickly too. That is not the rate limiting step in this process. The rate limiting step is from the glass to the crystal, the crystallization process. And mostly, as you probably know, that's really quite a slow process, right? It could take seconds, it could take minutes, it could be hours, right? In our case, it crystallizes in nanoseconds. Crystallizes in a nanosecond. So this is what I mean, a really bad glass. It is very thermally unstable. And so we've got two options. We could have a metastable phases, which is what we have here, crystal, glass, crystal, all metastable. And this will then form the base of a non-volatile memory, phase change, random access memory, where you store bits, 0 and 1, in the structure. So your 0 might be the crystal, which has got a high conductivity, and your 1 might be the glass, which has got a low conductivity. And this information is stored. Ooh, thank you very much indeed. Let's just try this. Thank you. Yay, look at that. Brilliant. Thank you very much indeed. Yeah, so you store the information here, not as electrons, as in CMOS devices, in flash or something like that, but as the atomic structure. The atomic structure encodes the information. So that, oops, I'm not used to it working now. So that's the metastable, or you've got the transient phase, actually this one here, and this is volatile. So the material only changes when you apply a voltage to it. So this is non-volatile. It remains off. You switch the voltage off. This is volatile. It's only on when you apply the voltage. So the sort of materials we're looking at are in this ternary composition diagram between tellurium, typically germanium, antimony, along this tie line between GT and sp2T3. Canonical composition is this 225 composition here, right? All these are congruent melting, actually. The composition doesn't change when it melts, because we're going through the melt, we're going from the crystal to the melt to the glass and back again. So we don't want the stuff to phase separate, which it does not. The stable crystal form of these materials is actually hexagonal, but we don't crystallize on the timescale of hours or minutes. We crystallize in nanoseconds, and so you get a metastable crystal, which is rocksalt, actually, this cubic phase, which is stabilized by having vacancies in it. So the motifs for rocksalt, remember, are 4 rings, cubes, 90-degree angles, octahedral 6-fold coordination, right? So you'll see those come up in a minute. And these metastable phases, glass is a semiconductor, resistive. Let's call that reset state. This cubic structure, crystalline, is conductive because it's actually a degenerate semiconductor, pretty metallic actually. So this is the on state, if you like, conducting state, and this is the off state. And these are very simple devices. They're 2-terminal devices. You have a top electrode, a bottom electrode, and your magic material in between, and you apply these short voltage pulses to switch the material between crystal to glass or back again. And here they are in a 3D cross-point array. So these blue lines are electrical conductor lines. These are the word lines, and these are the bit lines. So you apply voltages to the blue conductors here, and then if you've got a selector here, switch, which I'm going to talk about a bit later on, you can switch on or off individual pixel here, individual memories. And these memory units are what I've just been talking about. So these were commercialized a few years ago by Intel, Micron, using this geometry here. And it's faster, higher density than NAND memory. So let's just talk in 1 or 2 slides about, at the atomistic level, right down at the atomistic level, what this stuff looks like. Here's this composition, germanium, antimony, tellurium, 225. And here's a DFT model as it happens. And we analyze this to find out what the coordinations were. Normally in this business, what you do is to say, what's the first coordination number? You sit on an atom germanium and you have a cutoff and say, how many atoms of what type are within this spatial cutoff? And in some cases, like silica, that works really well because there's a really big minimum between the first and second peaks in the correlation function. Here, there's no minimum. It's rather arbitrary what you take as the cutoff. So we didn't use cutoffs. We used to say, actually, since we know everything about the electrons in the system, is there actually a bond between a given origin atom and its neighbours based on a thing called the electron localization function, basically what the electron density is. Is there a bond or is there not a bond? No. And if there is a bond, where is it? Or a lone pair. And what you find is the following. So for germanium, you find, as you might expect, tetrahedral germanium, no lone pair. So this is 4 means number of ligands and 0 is the number of lone pairs. So tetrahedral normally you expect, but there's another type of 4-coordinate germanium too, which is this one, which is defective octahedral with 180 and 90 degree bond angles. So it's an octahedron missing 2 neighbours. And you also see this dangling bond basically is 3-coordinate germanium. Antimony, you see similar defective octahedral sites, 4 and 5, no tetrahedral ones, but this trigonal one too, and tellurium, what you might expect, 2-fold coordinated, but also 3-coordinate. So actually quite a zoo of local coordinations, and importantly, remember this stuff crystallizes in a nanosecond or so. You don't have time in a nanosecond for atoms to move a long way to find the local crystal minimum. They've got to find it very, very quickly. And they do it because many of the atoms in the glass are already pretty crystalline-like. Remember, rocksalt crystal is octahedral, and here these units are all in the glass are already fairly octahedral. So just to blow up, this is what you see. You see these units here, defective octahedral sites, and they look a bit like a seesaw. Here's a seesaw, remember, a child's seesaw. Here's the plank and here's the fulcrum. These bonds here are long, weak, and strongly polarizable. And we believe they are basically 3-center, 4-electron. So these are not normal covalent bonds. These are 3-center, 1, 2, 3, 4 electrons distributed over those. And these are normal covalent bonds here. Because, why do I say that? If you look at, say, 4 naught here, these obey the electron octet rule. So I've got 4 bonds, each with 2 electrons, 4 2s are 8, right? Here I've got 3 bonds, 3 2s are 6, plus a lone pair of 2, 6 plus 2 is 8. All these obey electron octet rule, but these things like 4 1 or 5 1 don't, because I've got 4 bonds, 4 2s are 8, plus another 2 in a lone pair. 10 electrons in this unit, right? That is not obeying the octet rule. It looks as if you have hypervalency. Actually, the bonding is this rather special hyperbonding, which I'm not going to talk more about here, but talk later if you want. So just to then say that this glass, in the glassy state, it contains many crystallite-like units. Here they are, right, in the glass already. So you'd only need 1 or 2 atoms to move a very small distance to then make this, a crystal nucleus, basically. So this was our first, gap machine-learned potential, Gaussian approximation potential for GST. 58,000 configurations it was trained on. It's linear scaling, it's DFT accurate. You can build, we did then about a couple of years after it was made in 2018, 2020. We made this 25,000 atom model, which we're quite pleased with then, but of course this is rapidly looking rather small now. So, and this potential is transferable. It was trained basically on lots of different compositions. This is 225, but you can make GET, you can make sp2T3 with it. It's a sort of generic potential. Another advantage of this very fast potential is that you can make either quite a really big model in a reasonable length of time, or you can make lots of smaller models in a very short time. So you might say, why do I want to make an ensemble of 30 atoms, 30 models, each of sort of DFT size, 315 atom, when you can make something as big as this? Point is, you cannot do a proper DFT calculation, electronic calculation on something this big. You can only do it on very small models. So, to get around this, let's make lots and lots of them an ensemble and look at the statistics of this. And that's what we did. So we took 30 models of this 225, and we found this rather interesting, surprising behavior. So in the old days, it might take you 6 months just to make one model, 315 atom model. 6 months for a 315 atom model. Let's say you get this. You write a PRL, Phys Rev letter paper, saying there are no gap states in GST in my DFT models, right? Somebody else does another model, and they say, yeah, there aren't gap states, right? So what do you believe? Well, actually, what we found was 60% of the models actually have no gap states, 37% do. So it gives us some idea about the statistics of these things. So that was quite interesting. And then we started to analyze, so what is this saying? This is the density of states, this is the valence band, here's the gap, here's the conduction band, and these two models got basically the same band gap, but they differ by having this state deep in the gap here. So let's look now at a particular model. Here's the valence band again, here's the conduction band, density of states, here's a state deep in the gap, and I'm also, this is the density of states in black, I'm also showing the calculated, what's called inverse participation ratio, which basically tells you what the localization of electrons is at a particular site. So when this when this number is very big, it's very localized, and when it's small, it's delocalized. So small values deep into the band, delocalized states, just as you have in a crystal, except these are not block states, because this is glassy, of course. But at the band edges, and particularly in the middle, you have very strongly localized states. So due to disorder. So what does this deep gap state look like? It looks like this, actually. It's rather complicated. It's not a simple defect at all, as you have in silicon, say, where you just have an under-coordinated or over-coordinated atom. This is very complicated. The wave function, which is in green here, basically, you can see spreads all over here, and it's centered on a germanium, which is 5-coordinate, and there's another one here, actually, which is even 6-coordinate. This crystal-like little bit of glass seems to be the host for this deep state here. So that's the deep gap state, which are localized. What about these shallow, that is band edge states, which are also quite localized? What do they look like? They look completely different. They are small chains of these hyperbonded seesaw units. Okay, so here's a seesaw unit, here's another seesaw unit, right? Here's the fulcrum, here's the plank. These are the germanium atoms here. These are conduction band states. These are all conduction band states. These are from the gap model, and this is from a DFT model. So you can see the same in DFT or in gap, and the same at the valence band edge too. So why is this interesting? Well, because when you do the transformation from a crystal to a glass or vice versa, you apply a very high voltage, only 1 volt, but it's over maybe 10, 20 nanometers, so exceedingly high field for a very short time, and you pump loads of electrons and holes into the system, and it heats up, of course, but the electrons and holes can be themselves trapped. And this is how they can be trapped. So, oh my God, sorry. This is a conduction band state, bottom of the conduction band, and this is what you find in the glass, right? You then add 1 electron to the model, and this electron is trapped by this. This is the highest occupied, the highest unoccupied state. So LUMO, basically, lowest, the lowest unoccupied state. And this electron is trapped in this region here, and you can see this bond here has got a bit longer, and you send another electron in, so it's a 2-electron trap, and you should break this bond, right? So 2 electrons break a bond here. Here is a valence band state, top of the valence band, states are localized in this, and you trap 1 hole, and again, bonds get a bit bigger, 2 holes, it also breaks. So actually, this is essentially a self-trap bi-exciton scenario, basically. So these states can trap electrons and holes quite easily, and that has an impact on what the conduction process is. Um, seem to be jinxed here, actually. Let's just try and go back. Yeah. Can you do? Oh, yeah, we go. Right. Okay. That was then. Now is now. So we've got a latest machine learned potential, GST, based on a different structural descriptor, atomic cluster expansion, and it's 3 orders of magnitude faster than what we had before. So we can now simulate million atom models for 50 nanoseconds, and we actually tested a billion atom at DFT accuracy, and we can find that actually, we can have a reasonable number of time steps just actually on just 8 nodes, basically. Actually timing, doing the calculations is not a problem. Actually storing the data from an MD simulation of a billion atoms is actually the limiting step at the moment, basically. We just don't have enough memory to do this. But we've done million, and we can do a billion. Just let me skip that. So this is the application. So here is a blow-up of that cross-point memory array I showed you earlier on. Here are the word and bit lines. Here's the memories here with a 0 and a 1 stored in it. Here it is again. Here's the switch. Here's the GST memory element. And typically, this is 20 by 20 by 40 nanometers in a real device. So we wanted to actually do a device-level simulation. Here it is. Here actually is a model of 20 by 20 by 40. And this is what we start with. Single crystal in here, logic state 1, and we apply heat to it, and we can just melt it. And depending on how fast we do it, this melts in about 50 picoseconds. So this is the initial reset process, going from crystal to melt, and then if you quench that down equally in a sort of similar time, it'll go to the glass. Here we are in the glassy state, and we are heating it up, and this is how long it takes to crystallize, 20 nanoseconds, which is what the experimental time scale is, in this device size box, basically. And you can see that it starts with a glass and you end up with a polycrystal, and then, so this is logic state 1, and then we can heat this up again and melt it and so on, go round the loop. So we can do simulations at the device scale, and this is 500,000 atoms doing this, 500K, all at DFT accuracy. Could I have another slide, please? Thank you. So, how do these things crystallize? There are 2 ways of crystallizing. One is that the blue is the glass here, yellow are the crystals. You could have sort of spontaneous, homogeneous nucleation here. That you have to have a certain number of atoms forming little crystal nuclei before they start to grow. This is nucleation driven, and you get lots and lots of very small crystals. Or it could be growth driven, that basically often is just templated out from some interface, and growth is the limiting step, not nucleation. And this is interesting and important because the rate of nucleation or rate of growth occur at different temperatures. Right? So if you are at a temperature here, you just will nucleate more than you grow, and here you will grow more than you nucleate. And so we did the same simulation in this device size thing, crystallizing at 550K here. And you can see this, this is starting at 3 nanoseconds. It started amorphous, right? 3 nanoseconds, you're starting to see the nuclei formed, and you form basically a polycrystalline array with very, very small crystals, because this is nucleation driven. If we then anneal not at 550 but 650K, we're here now, and we're in the growth limit. There are very few, basically no nuclei here forming, and eventually, as soon as you form one, the thing just grows. So you get a completely different morphology depending on what the temperature is. And people knew this. I mean, people know that crystallization behaves like this, but nobody's actually seen it in simulations before. And you can only see it at this sort of size, because look at the size of the crystallites here. They're comparable, basically, to the size of our box. Can I have the next slide, please? Thank you. So the last one I want to talk about, this is Bilger mentioned neuromorphic brain-like computing, basically, where you don't just have binary bits, 0, 1. You have a continuum of states going, in our case, going from 100% glass to 100% crystal continuously. And you can have a cell like this, where basically this is all crystal, and you're just making a dome or mushroom of glass, and it gets bigger and bigger and bigger. And of course, these have different conductivities. So you have a continuous range of conductivities, but depending on how much you program this region here. So this is typically what they look like, 100 by 100 by 40 nanometers in a real device. We can't do that at the moment. So we took a slice. The area is right, 100 by 100, but then we took a 5 nanometer slice through the middle. That's already nearly 1 million atoms, actually, 800,000 atoms. And this is what it looks like. And we can program different regions. So we can, here's a single crystal, and we can melt it and then recrystallize, and we have a bigger amorphous region, and we can crystallize that as well. So we're now looking at this way of trying to store more data, basically, in a continuous way here. And I should say, while you're looking at this, people thought up to now that this device was only determined by the proportion of crystal, conducting crystal, to resistive glass that you had, just that ratio. Actually, that can't be true. It is partly true, of course, but it can't be only true because you've got these polycrystals here with all these grain boundaries, and you can control the grain boundary size by what the temperature is, your crystallization. So these grain boundaries will also have their own resistivity behavior, and that's an extra level of control that you can have. I've talked about memory. I now want to talk about the switch, because without the switch, you can't just write individual memory cells here. And in the devices that are being used at the moment, they use these rather complicated chalcogenides, and the on state here is just an electronic effect. It's just electron trap filled. We discovered 2 or 3 years ago that actually you could do it with an element, single element tellurium, and that switches. So here you have a top electrode, titanium nitride, a bottom electrode, titanium nitride. Here's tellurium, about 10 nanometers thick. And this is what happens when you apply a voltage. First time, you're in the crystalline state. It is semiconducting. And initially at about 2 or 3 volts, then suddenly you melt the tellurium. And molten tellurium is liquid tellurium is a metal. You suddenly switch on this very highly conducting state here. So it looks here a negative differential resistance. You're just switching from one path to another. So this is off, semiconducting crystal. This is on the metal. And of course, when you switch the voltage off again, the liquid crystallizes and you go back to the on state again. So you can see the very first time you do it, you need a threshold voltage, a fire voltage of about 3 volts. Subsequently, second, third, fourth, you only need about 1 volt, right? Why, which is good, but why this difference? And this just shows you won't be able to see, can't even see it here right at the back, but this intermediate state, the on state here, we've done in situ TM, and actually you do see that the stuff melts and then crystallizes again to a polycrystal, having started as a single crystal. Sorry. So we did a simulation of this. So this is the original on state, single crystal here, and you need a threshold voltage to melt it. So this is what we found in the simulation. This is a 100,000 atom simulation here using this ACE potential. And the stuff melts at about 723 Kelvin. Look at the mean square displacement. Nothing happens. It's in the crystal solid, and then it suddenly melts here. This happens to be, amazingly, the experimental melting temperature, right? So we can reproduce the experimental melting temperature, starting with a single crystal. So we have the melt, and then we quench the melt, and what you end up with is a polycrystal now. And this, let's do the cycle again. Let's heat the polycrystal up, and what happens is that actually, with lots of grain boundaries, the stuff melts at a much lower temperature, like 200 degrees lower than the single crystal. at 500K rather than 700K. So a lower melting temperature means you need a lower power, you need a lower threshold voltage in order to melt. So we believe that this transition from this high voltage to this low voltage is simply due to the fact that you have this grain boundary induced melting subsequently for all these states here. I would tell you something else if I could change the slide again. Right, here we go. How much time have I got? Do you want me to stop? It says 1 minute 30. Let me just very, very briefly talk about, again, tellurium. Crystalline tellurium is a chain structure, helical chain structure, and it could have a helix this way, right hand, or it have a helix this way, left hand. These are chiral. They're not superimposable. So the question is, how does chiral tellurium crystallize? And it's been proposed in a long, long time ago that maybe there's a cubic intermediary. If you have a cube, which is symmetric, and you squeeze it in one way, then you actually get 3 short and 3 long bonds, or squeeze another way, you get 3 short long bonds another way, and actually you can generate these helices through this cubic intermediary. And we did a simulation just to see this. So here we have 100,000 atom model of the glass, and basically nothing happens really for about a nanosecond, and then we start to see something happening, and we see some nuclei, and we look at them, lo and behold, these are cubic motifs coming up, cubic motifs, right? So for between 1 and 3 nanoseconds, basically these cubes appear more and more, and then suddenly, 4 nanoseconds, you go from cubes to chains, switches. And these then chains just grow more and more. So these are chain structures showing where the crystals are. So crystals here and grain boundaries here. This is color-coded to show you what the type of chirality is. Are they left or right? And you can see that actually you're getting both right and left forming in equal proportions here. So this is all crystallizing at 300K. And then if we just carry on from that state, if I can show you. Next slide, please. Thank you. If we then increase the temperature to accelerate things and look at what's happening, these grains get bigger and bigger, grain boundaries get smaller and smaller, and we end up with just 2 grains in our humongous model, one right, one left, racemic mixture. Okay. And it's quite interesting what's happening. You're getting chiral transfer at grain boundaries. Here's a grain boundary between right and left, stuff in the middle, and you get a statistical fluctuation. You get these cubes formed, and then basically this blue then just grows through the red region. Or, alternatively, you could have happening within a grain. You could have these chains here moving this way. You get a fluctuation, you get some cubes formed again, and then actually you get a completely orthogonal growth of the other type of chirality. Right? So I should stop. I've got 35 seconds, so I'll let you read. Thank you very much indeed for your time.
Thank you. Thank you. Any questions? Anybody?
Stephen, I think that's absolutely fascinating talk, and we do very similar things, and we're always pushing up against the boundaries of how many atoms you have in your models.
Yeah.
So with your DFT, you talked about having 315 atoms and doing 30 variations of that.
Yeah.
If you go to more atoms or less atoms, do you see a difference? Like, have you tried it going? Because it sounds like you can get up to 50,000 or 500,000 atoms. So if you went to like 100,000 or rather than 315. Is that possible with DFT now or not?
Yeah. Well, we can. We've made, to answer your point, that was then. I've given you a sort of timeline. That was then. That's all we could do then, right?
Yeah.
But we do need to look at small model. I'll just come back to the bottom bit here, talks about that. But we've done multiple models of this million atom silicon model, for instance, right?
Yeah.
Not 30, but 3 or 4. And, and they behave exactly the same. So, you already got economy of scale, basically. Look at a million atoms, but actually you have to worry, well, am I getting trapped in a particular local minimum here? But not really, no. But the problem is we have these humongous models, and if If you look at atomic properties, that's okay. If you look at electronic properties, not okay, because all we can cope with are 300 atom models, right?
Yep.
Directly. So what we've done is that in this paper that's referred to here, we've done machine learning not only of the potential, but of any other property, particularly the electron density of states.
Okay.
So we machine learn, and we can then...
So let me ask one more question then. So I think you had a slide where you compared the DFT with the machine learning.
Yeah.
And you had a graph with the number of atoms, and I can't remember what was on the vertical axis, but it looked like there was a difference for the same number of atoms. You had a difference in energy, or?
Ooh, I can't remember what that would be.
It's kind of like right in the middle of your talk.
Right. Things that work it right.
Got to go quite far back.
Far back. No, sorry.
Before the crystallization. Before this.
I can't think what that was.
That's it. There.
No, that one.
That
okay.
one there. So you see
okay.
you had the blue curves, so it's.
Oh yeah. Okay.
induced
Well, this is
today.
just telling you how
I see.
fast. Sorry,
Okay,
that's
just the
all.
Speed. Okay.
Speed of the thing, right? There's your 1,000 atom speed up, right? So for 1 million atoms for gap, oh my God, 1 million atoms for gap, that takes this time up here, and for the other thing, you can just do it in red, right? Basically, so yeah.
Got you. But the actual magnitude of the energies or whatever you get out are the same. Yeah.
Oh, the same.
Yeah,
Yeah.
okay. That's great.
Yeah, it's DFT accurate. Whole thing's
Excellent.
DFT
Okay,
accurate.
fascinating.
Right?
Thank you.
Yeah.
Yeah, usually the fitting is to what, 1 MeV or something?
Yeah. It's about 2 MeV per atom.
Okay. The business you showed about the nucleation of the left and right-handed and the grain boundary, that is effectively a soliton. So it doesn't require a lot of energy to move, and that's why you eventually see it crystallizing out.
Yeah.
If you use a one-dimensional model or a few dimensional models, it maps onto a soliton.
Soliton.
Soliton
Yeah,
moving up
that's
and down.
cool, yeah. We found that actually, you're only 90 MeV per atom higher in the cube than you are in the chain, actually. So it's a very, you do go through this, but it's a very low barrier, actually. So
Yeah. Any other question? Andrew?
Thanks, Stephen. Lovely talk. When you were referring to the temperature and the correlation with the switching time, is that current driven?
What?
Well, the voltage, you said a certain voltage is needed.
Yeah.
That's thermal.
Oh yeah, absolutely. Everything's thermal. Yeah. Actually, both for the memory, it's thermal. So we're going from the crystal, we melt it, switch the pulse off, get to the glass, go to the crystal, you heat it, all voltage, Joule-heating.
Yes.
Same with the tellurium switch, just the same, yeah.
Oh,
Yeah.
Thank you.
Yeah.
Is there a last question? Yeah, down here. There you go.
Yeah, very nice talk. I have just one question. What is the switching time when you talk about the neuromorphic computing application for this kind of material?
What's the switching time?
Switching time, and what things limit the switching time for this?
Oh, well,
neuromorphic applications, yeah.
Sorry, the last bit of your question, what limits the switching time and?
For the neuromorphic computing
Neuromorphic,
application.
yeah. Well, neuromorphic is just like the other thing, actually. It's except you have this continuous range of glass to crystal, right? It's not 100%, 100%, continuous range. So you're still worrying about how long it takes to switch between a crystal and a glass, right? That's the limiting stage. And it's material limited, as I've shown you here, like 10 nanoseconds, 5 nanoseconds. Okay. Doesn't matter if it's neuromorphic or flash type memory. We found that actually about 10 years ago, I suppose, if you can prime the material, you send in a small voltage, which is not enough to switch it, but it actually nucleates the material. And then we showed that, what was it, about 50 picoseconds we can switch it actually. So it's a more complicated pulse sequence, but that gets around the intrinsic material limitation. So this material is quite fast actually. 5 nanoseconds to crystallize is pretty fast, but and it's certainly fast enough for DRAM replacement, actually. So we've got a non-volatile answer for DRAM. So, we're talking about sustainability, means you don't have to boot up your computer, right? So, it's always on, basically, and so, yeah.
Okay, thank you.
Okay.
Okay, let's thank Stephen, and we'll move on to the next speaker.